Our today topic is gain, attenuation, and decibel and noise. So gain, attenuation, and decibel can be found in chapter 2. Noise is a little bit explained more in chapter 9. I put all together here. And so other than these two topics, I am a little bit covering some additional topics in chapter 2, which are filters and Fourier. So just for your information, some of them. Okay, so these topics fall into your first and second learning outcome. Yeah, again, it is from Frenzel book. Yeah, chapter 2 and a little bit on chapter 9. Okay, so as we said, we talk about gain, attenuation, decibels, and noise. It's come from chapter 9.5. I have a little bit filters and Fourier theories, just very introduction one, because it's not within the syllabuses of your subject, but I just want to include a little bit for your next topic, so at least you are prepared. Okay, so in most communication or electronic communication, we try to modify the signals to produce a desired result. We want, so that the target what we want in terms of communication performance, we design the signals and the system so that they can be suitable for the system and also to achieve high performance. So in most circuits, we have gain and attenuation. So attenuation is something almost can be avoided. So gain can be available in a circuit or can be not, but most of the circuits, sensors, communication systems, many other circuits, gain usually exists as well. So what is gain? So gain means amplification. It is the ratio of the circuit's output to its input. So as the equation shows, so the output elements divided by input. It can be voltage, for example. So usually it shows by this triangle, means representing we are amplifying. Or it could be in terms of power, which we will see a little bit later. For example, if the input is 150 microvolts and the output is 75 millivolts, so what is the gain? So we divide output, which is 75 millivolts, 75 times 10 power of minus 3 divided by 150 microvolt, which is multiplied by 10 power of minus 6. So we have 500. So there is no unit because gain is both output and input elements are same units, so is unitless. So then in another example, we have 0.6 volt as an output and we have 240 gain. We want to find the input. So we have 0.6 divided by 240 gain. We have 2.5 millivolt as the input. So our input was 2.5. The gain was 240. So then it become 0.6 volt output. I have one example here for you guys. I want you to solve. I give you just few minutes. So the output voltage, 750 millivolts. We convert it to voltage by times 10 power minus 3. And then we have input voltage 30 microvolts. We convert to volt as well. So by multiplying 10 to minus 6, so we have 25,000 gain for this amplifier. Yes, then as we said, most amplifiers are also power amplifiers. So the same procedure can be used to calculate power gain. So here it shows as AP, where P in is the power input, P out is the power output. So now here we use the ratio between output power over input power instead of voltage. So here I have one example. The power output of an amplifier is 6 watts. The power gain is 80. What is the input power? So similarly, we have our equation P out over P in providing gain. We can write P in equal to output power divided by the amplifier gain. So then what we have is 6 watts divided by 80, we have 75 millivolt input. So that is how we can use for power. An amplifier is cascaded when 2 or more stages are connected together. So maybe in a system, you have few amplifiers joined in series, they call it cascaded. The overall gain is the product of the individual circuit gains. So here there is one example. Our input is 1 millivolts. The gain of first, second, and third amplifiers are 5, 3, and 4. So when the signal comes in, 1 millivolt come in, multiply by 5 as a gain. So then the output will be 5 times 1 will be 5 millivolts. The unit follow the unit of your input or the voltage, because gain has no unit, is unitless. So then 5 millivolts going to the input of the second amplifier. We have a gain of 3. So then 3 times 5 giving us 15 millivolts output from the second amplifier. And then the 15 millivolts applied to the third amplifier, which has a gain of 4. 15 times 4 will be 60 millivolts. So you can see our voltage was 1. The output becomes 60 millivolts. So how this works, if we can multiply all the gains in the system, which is 5 times 3 times 4. Here, the amplifier gain of amplifier 1, amplifier 2, and amplifier 3. So 5 times 3 times 4 becomes 60. So that is the gain. So you can directly multiply 1 times 60, the output give you 60 millivolts. So we have one example here. 3 cascaded amplifiers have power gain of 5, 2, and 17. So means these 3 amplifiers are series together or cascaded together. The input power is 40 milliwatts. What is the output power? What we do is the 3 gains of cascaded amplifiers are multiplied together, which is 5 times 2 times 17 become 170. Then we have this equation, our output power, if we solve the equation for output power, we have gain times input power. So 170 gain times input power of 40 milliwatt. So the milliwatt we multiply by 10 power minus 3. So then we have 6.8 watt. I have another example. A two-stage amplifier has an input power of 25 microwatts and an output power of 1.5 milliwatts. One stage has a gain of 3. What is the gain of the second stage? So this means we have two amplifiers cascaded. So the gain of one of them we know is 3. We want to find what is the gain of the second amplifier. We also know the input and output powers. How we can find the gain of the second amplifier. So I give you 1 or 2 minutes. Let's see how we solve this. We can find our gain. So this gain is the total gain of the system. We have output power divided by input power, 1.5 milliwatt. We multiply by 10 power of minus 3 divided by 25 times 10 power of minus 6, as 25 was microwatt. Then we have total gain of 60. So since the first gain, amplifier has a gain of 3, total gain is 60, equal to 3 times A2, the gain of second amplifier. Then we can solve for A2 is 60 over 3 become 20. So we have one amplifier has 3, gain of 3, another one has gain of 20. Okay, so this was about gain. Now let's talk about the attenuation. Attenuation refers to a loss introduced by a circuit or component. If the output signal is lower in amplitude than the input, the circuit has loss or attenuation. So this is unlike the gain. In the gain, the output usually is larger than input. But for attenuation is other way around. So the output is smaller than the input. So the letter A is used to represent attenuation, and it is again similar to gain, is output divided by input. It can be voltage or it can be power. Circuit that introduce attenuation has a gain than the gain that is less than 1. So if you calculate gain for a system and the value becomes smaller than 1, means is attenuation, means is not gaining, is attenuating or loss the power in the system. Here is one example of attenuator. For example, for electrical circuit, you have input voltage. So the voltage applied to this circuit going through first resistor. Then our output power is at the middle of the two resistors. So the first resistor has 200 ohm, second one has 100 ohm, and we can find the attenuation of this system. So of course the attenuation means we see what is the output voltage. We know when there is a voltage applied in this circuit, some voltage will be dropped on resistor number 1, and then your output voltage is something smaller than input voltage. So that means your voltage has been attenuated or lost in the system. So how we calculate this? So we write a voltage divider. So V out equal to V in times R2 over R1 plus R2. Then what is gain is output over input voltage. So if you solve this equation, so to get V out over V in, then the resulting equation is R2 divided by R1 plus R2. So the gain for this system or such attenuators is just R2 divided by R1 plus R2. Then R2 is 100 divided by 100 plus 200 ohms. So the gain or attenuation of your system is 0.33. Now in this case, if a signal of 10 volts is applied to the attenuator in this figure, the output is, we are looking for the V out, the gain is available, which is 0.33. V in is available, which is 10. And we know gain is V out over V in, which is equal to this equation of R2 over R1 plus R2. But since we already have this value, we just solve the equation for V out, which is gain times input voltage. So 10 times 0.33, so then you have 3.33 volts. The output voltage you can see is from 10 volts, it becomes 3.33 volts. With cascaded circuit, the total attenuation is the product of the individual attenuations. Similar to what we said in gain, it will apply to attenuation as well. So here, for example, we have a system. There are 3 stages of losses. So loss of a stage or first loss is there is a loss of 0.2, magnitude of 0.2. Another loss for circuit is 0.9, and the third loss for a component maybe is 0.06. If we have input voltage of 3 volts, what is our output voltage? So the 3 losses can be multiplied together. So the product of 3 of these losses, 0.2 times 0.9 times 0.06, giving us 0.0108. So this is total loss of the system. Since we have the input, then the output is input times the loss. Then we have 32.4 millivolts. So 3 volt input giving us 32.4 millivolt output. So that is our loss calculation in cascaded attenuation. I have another example here. We have attenuation and also gain. Both of them are available in the circuit. But this is designed, the gain exactly offsets the attenuation. So we put the amplifier to fully offset the amount of attenuation in the circuit. We have 750 ohm first resistor, and the second resistor has 250 ohm resistance. So then we can find the attenuation, which is R2 over R1 plus R2, 250 over 1000. So we have 0.25 attenuation. So then to fully offset the attenuation, we put a gain of 4. So then the amplifier has a gain of 4. 0.25 times a gain of 4. Then it gives us the total gain or attenuation of 1. So then output power will be exactly the same as input. A voltage divider, such as what we've seen in this example, so has values of R1, 10 kilo ohm, R2, 470 ohm. What is the attenuation? So we can calculate the attenuation. So R2 over R1 plus R2. So 470 ohm divided by combination of these two. So this is 10 kilo ohm means 10,000 plus 470 become 10,470 ohm. Dividing these two, we have an attenuation of 0.045. What amplifier gain would you need to offset the loss for an overall gain of 1? So our overall gain is 1. Attenuation number 1 is available. We need to find A2, which is in fact our gain. So where A1 is the attenuation, A2 is the amplifier gain. So then we have 1 equal to 0.045 A2. So A2, we solve for A2 will be 22.3. So that is our gain. So if we put such amplifier in the system, the input voltage will be the same as the output voltage. Note, to find the gain that will offset the loss for unity gain, just take reciprocal of attenuation. So means A2 is 1 over the attenuation. So then you can find your gain. Okay, so one more example. I have now a system which some few losses and attenuation, gaining happening in the system. Let's see how to solve this. I have input of 1.5 volts. I have one stage loss of 0.1 attenuation or loss. Then my output become 1.5 times 0.1 becomes 0.15 volts. I put a gain amplifier with a gain of 10, which is opposite to the attenuation. So it just satisfied or offset the attenuation. So then you got the same voltage as the input 1.5 volts because 0.15 times 10 become 1.5 volts. Then you have another loss of 0.3. So 1.5 times 0.3, we have 0.45 volts. So then we have an a gain of 15. 15 times 0.45 volt, we have an output of 6.75 volts. So that is our output voltage. If we want to find the total gain of the system, when we say gain, is mixture of gain and attenuation here. So A1 times A2 times A3 times A4, 0.1 times 10 times 0.3 times 15, giving us 4.5 total gain of the system. So if you multiply 1.5 times 4.5, you should get 6.75 as we see here. Okay, I have one example for you. An amplifier has a gain of 45,000, so which is too much. for the amplification. With an input voltage of 20 microvolts, what attenuation factor is needed to keep the output voltage from exceeding 100 millivolts? So we don't want our output goes more than 100 millivolts. Our input is 20 microvolts, but we have only an amplifier of 45,000. So let's say there is no available other amplifiers. So what attenuation we need to put in this system to make sure the output is not exceeding 100 millivolts? So we take A1 as amplifier gain of 45,000, A2 attenuation factor of our what we want to find, the attenuation, and total gain is 80. So you guys, with this explanation, solve this and share what is your answer. So first, we find the total gain of the system. We have output voltage divided by input voltage, 100 millivolts divided by 20 microvolts, we have 5,000 gain. So since our total gain we know is 5,000, we know our amplifier gives us 45,000, we can find the attenuation. So then we solve for A2, which is total gain divided by A1. So 5,000 divided by 45,000, we need an attenuation of 0.11. Okay, so let's see what is decibels. The decibel we usually show by dB. D is a small letter, B is capital letter, is always the same. So you should follow this, is a standard form of showing the decibel. Is a unit of measure used to express the gain or loss in a circuit. Originally, decibel was created to express hearing response, and it is 1/10 of a bell. So you know Bell is Alexander Graham Bell, so who is the inventor of the telephone. So this bell comes from there, so from his name. So when gain and attenuation are both converted into decibels, the overall gain or attenuation of a system or circuit can be computed by adding individual gains or attenuations. So they are expressed in decibels. So the equation, because decibel in logarithmic base, multiplication in logarithm form, it becomes just summation. So here we have decibels for different parameters, for voltage, current, and power. If you want to convert your gain, before this we was talking about the gain, which was, our gain was, for example, output voltage divided by input. So now if we want to convert this to decibel, or we right away use output voltage divided by input voltage showing in decibel, this is the equation. 20 times log base 10 of output voltage divided by input voltage, or this can be just your gain. For current, you can have same equation, output current divided by input current. So log base 10 of this divided by 20. But when it comes to power, the gain or attenuation is 10 times log base 10 of output power over input power. I want somebody explain why for voltage and current we have an coefficient of 20 times log, but why when it comes to power it is 10 times log. So anyone can explain in electrical system or circuits. So what we have is usually we express V square over R. Then if you want to use V out over V in for a system, so then the R will be in a system, for example, either unity or we cancel this. So then your V over V for a ratio will be squared. So that's why this square in logarithmic form come to the front side, and we have 2 times 10, which is supposed to be originally 10 times log of P out over P in. So now if you take out P out, put V2 over R, P in V in over R. So then this squared is the one coming to the coefficient. So then you have 20 log times V out over V. Same goes for the current. So if you write P out as Ri square for the output volt current, input current you write also R times I in square, then your equation have the square, which is the 2 goes to the behind of the log, so become 20 log I out over I in. Okay, so these are the way you can convert your gain to decibel. So we have one example here. An amplifier has an input of 3 millivolts and an output of 5 volts. What is the gain in decibels? So we write that equation, 20 log base 10 of 5 volts divided by 3 millivolts. So 3 millivolts we convert to volts, becomes 0.003. Then we have 20 log of 5 divided by 0.003 is 1666.67. If you take log base 10 of this will be 3.22 multiplied by 20 is 64.4. So that is your gain in decibel. So now we call it, this system has a gain of 64.4 dB. B is a filter has a power input of 50 milliwatts and an output of 2 milliwatts. What is the gain or attenuation? Filters are those usually cut your input and the output will be something narrower in bandwidth or maybe in voltage or power. So then here, since we have in power, we use the power equation, which is 10 log of P out over P in. So we have 10 log of 2 milliwatt over 50 milliwatt. Since they are both same unit, we can just keep them. So we have 10 log base 10 of 0.04. log of 0.04 become a negative value because it's smaller than 1. So then 10 times minus 1.398, we have minus 13.98, means we have an attenuation or loss of 13.98 dB. Note that when the circuit has gain, the decibel figure is positive. If the gain is less than 1, which means that there is an attenuation, the decibel figure is negative, as we seen in this example. Okay, one more example. Total gain or attenuation in the algebraic sum of the individual stage gains in decibels. So I have a gain of 15 dB. I have an attenuation of minus 20 dB. And I have another amplifier with gain of 35 dB. So what is the total gain of the system in decibel? You just combine them or sum them, add them. So 15 minus 20 plus 35. So then we have 30 dB gain in this system. So why we say gain? Because the final value or the total is positive. What is anti-log? So sometimes we have a value we have a gain or attenuation in decibel. We may have input or output voltage or power. Then we want to find the other input or output value. But since P out and P in are in the equation in the log base, in the logarithm form, so then if we want to calculate to find the parameters of input and output parameters, we need to do anti-log. So the anti-log is the number obtained when the base is raised to the logarithm, which is the exponent. So how it is? So as I said, anti-logs are used to calculate input or output voltage or power given the decibel gain or attenuation and the output or input. So attenuation and one of the input or output is provided. We are looking for the other input or output. So the anti-log is the base 10 raised to the dB over 10 power. This is for power, okay? dB over 10. But if it is for voltage, it's dB over 20. Or the same for current also, dB over 20. The anti-log is readily calculated with a scientific calculator. So here I am showing you. So I have n equal to 10 power of y, and y is equal to log n. So this is a standard relation between log and anti-log. So how it works in fact is I divide both sides of the equation by 10 first to derive this coefficient of 10 behind the log. So then I have dB over 10 equal to log P out over P in. So then we can use this equation, which is similar to this. If we do anti-log from both sides, so then this log and anti-log will be cancelled. So remaining is P out over P in. And the other one will be anti-log dB over 10, which means log power of minus dB over 10, which you can see here. This means anti-log of dB over 10. If you have your decibel value, which is the gain or attenuation, divided by 10, then you get anti-log of this. So then you can find P out over P in. This is the same as 10 rise dB over 10 or 10 power of dB over 10. So we have one example to understand this better. A power amplifier with a 40 dB gain has an output power of 100 watts. What is the input power? So now we write our general equation, dB equal to 10 log P out over P in. We divide both sides of the equation by 10. We have dB over 10. Remaining the other side log P out over P in. So then we substitute the values 40 gain over 10 equal to log P out over P in. So then we have 4 equal to log P out over P in. Here what we did, from both sides of the equation, we applied anti-log. So we have anti-log of 4. The other side, we have anti-log of log of P out over P in. Anti-log of a log will be just cancelled, become just remaining P out over P in. The other side, anti-log of 4 means log minus log inverse of 4. Log inverse of 4 means 10 rise 4 or 10 power of 4. So then our P out over P in is 10 power of 4, which is 10,000. So now we substitute our output power, which is 100 watts divided by P in equal to 10,000. To solve P in, we have P out over 10,000, 100 divided by 10,000. So our P in, we got 0.01 watt or 10 milliwatt. So means in this system, we apply 10 milliwatt power. Since we had a gain of 40 decibel, the output become 100 watts. I have one example for you guys to solve. An amplifier has a gain of 60 decibel or dB. If the input voltage is 50 microvolts, what is the output voltage? So I give you few minutes, you solve this. Since we have our equation for decibel, for voltage is 20 log V out over V in. So we first divide both sides of the equation with 20. So we have decibel divided by 20 equal to log of V out over V in. So then we can solve this. So then we have, as we said in previous example, V out over V in equal to log inverse or log rise minus 1 of decibel over 20, or can be represented as 10 power of dB over 20. So this 10 comes because this log is log base 10. So then we have 10 rise dB was 60 divided by 20, so is 10 power of 3 become 1000. So V out over V in equal to 1000. So we are looking for the output voltage. So then we solve for output voltage will be 1000 times input voltage. So 1000 times 50 microvolts, 50 times 10 power of minus 6 times 1000 gives us 0.05 volts or 50 millivolts. Other than decibel, we also have something called dBm. So when a decibel value is computed by comparing a power value to 1 milliwatt, the result is a value called the dBm. So this is a useful reference value for many systems which they have very low power. For example, in optical fiber communication or in optical systems, the powers usually are very small. The powers usually represented by dBm. Same for many sensors or electrical systems or circuits. When the power is too low, we show by dBm. The equation is this: the power, which is in watt, divided by 0.001 or 1 milliwatts. So that is how we do the equation. But the answer is dBm. Remember, if you have a system, the input is dBm, then you have a gain, let's say, gain is always in dB, and attenuation always is in dB because they are in ratio form. So then if you multiply a power in dBm multiplied by a gain of dB, your output still is dBm. So this is something you should remember. I have one example here. If a microphone has an output of minus 50 dBm, the actual power, which in power or watt or milliwatt, we can calculate as shown here. So minus 50 dBm equal to 10 log P out over 0.001, representing milliwatt. We divide both sides by 10. So then I have minus 50 dBm over 10 equal to log P out over 0.01. Then P out over 0.001 equal to 10 rise minus 50 over 10, which become minus 5. Then I can solve for P out, which is 0.01 times 0.401. So which is, we can write 10 rise minus 3 times 10 rise minus 5 equal to 10 rise minus 8 watts. This is equivalent to 10 nanowatt. So means this microphone has 10 nanowatt output, which is equivalent to minus 50 dBm. Okay, I have one more example. A power amplifier has an input of 90 milliwatt across 10 kilo ohm. The output is, so this is for inputs. The output circuit is 7.8 volts across an 8 ohm speaker. So what is the power gain in decibels? So you must compute the input and output power levels first. So it's just advising what we do. So we can first calculate the power in the input. So we have voltage and the resistance in the circuit for input circuit. So we have V square over R. So 90 millivolts, we convert it to volts, which is 90 times 10 raised minus 3. The whole thing squared. So divided by R, which is 10 kilo ohm, means 10,000 or 10 raised 4. So then we have 8.1. 8.1 comes from 90 squared. So then times 10 power of minus 7 watts. So this is P in watts. So for P out, we have the voltage, we have the speaker resistance, which is 8 ohm. So we have 7.8 volt squared divided by 8 ohm. We have 7.605 watts. Now P in and P out we have in watts. So we want to find the gain in decibels. So we find the gain ratio first. So is P out over P in. So 7.605 divided by 8.1 times 10 power of minus 7. We have 9.39 times 10 power of 6 gain. This is our gain factor. So then the gain in decibel is 10 log of the gain factor, or the gain ratio is equal to 10 log of 9.39 times 10 power of 6 is equal to 69.7 dB or decibels. So that is our gain. So gain in normal form is 9.39 times 10 power of 6, but in decibels is 69.7 dB. So both of them are two values or two ways you can represent the gain of a system. Other than dBm, we also have dBc. The value dBc is a decibel gain or attenuation figure where the reference is the carrier power. So, for example, if a message signal is 1 milliwatt compared to 10 watt carrier, so then dBc is, so we have dBc equal to 10 log of the signal power over the carrier power. So is signal power was 1 milliwatt, we shown 0.001 divided by 10 watt, which we write 10. So then 0.001 over 10 become log of this become minus 4 because it's smaller than 1. Then 10 times minus 4 is minus 40. So our dBc is minus 40. I have one example here. An amplifier has a power gain of 28 dB. The input power is 36 milliwatt. What is the output power? Okay, so we can write the equation P out over P in, 10 raised decibel over 10, because these are power. So decibel value is 228 divided by 10 will be 2.8. So we have 10 raised 2.8, which is 630.96, equal to P out over P in. To find P out, we have P in times 630.96. So our P in is 36 milliwatts, means 36 times 10 power minus 3. So then we have 22.71 watts. I have one more example. So a circuit consists of two amplifiers with gains of 6.8 and 14.3 decibels, and 2 filters with attenuations of minus 16.4 and minus 2.9 dB. If the output voltage is 800 millivolts, what is the input voltage? Okay, so first we combine all the gain and attenuation of the system because they are in decibels. They combine them, they sum together, A1 plus A2 plus A3 plus A4. Attenuations, we put negative, gains, we put positive, 6.8 positive plus 14.3 minus 16.4 minus 2.9, we have 1.8 dB gain. Is positive, so it's gain. So then we know the gain is equal to V out over V in. If we want to write in decibel forms, V out over V in is 10 rise decibel over 20 for the voltage. So then we have 1.8 our gain divided by 20. We have 10 rise 0.09. So then our V out over V in is equal to this value, which is equal to 1.23. So means this 1.8 dB in normal is 1.23. So now we have output voltage, 800 millivolts. Then we can find input voltage. So the voltage input is equal to output voltage over this gain factor of 1.23. So 800 millivolts over 1.28, giving us 650.4 millivolts. So this is our voltage input to the system. I have one more example. Express P out equal to 12.3 dBm in watts. If you want to show this in watt, what is the value? The equation of dBm is 10 log P over 1 milliwatt. So then we solve for P over 1 milliwatt, which is P out over 0.001, which is equal to 10 rise dBm over 10. Our dBm is 12.3 divided by 10 is 1.23. So 10 rise 1.23 becomes 17. So then P out is 17 times 0.001, which is 17 milliwatts. So making power measurements, the use of microwave power meters allows RF designers or technicians to make measurements typically from minus 30 dBm to plus 20 dBm measurements. So this is a measurement device which we can measure the power. By adding attenuators, higher power measurements are possible. So in some cases, if the voltage is too high, you cannot put directly your instruments. So you may need some insulator and insulate the high voltage to low voltage. At the same time, your high voltage can be applied to one side, is inside like a transformer or some attenuator, convert to low voltage so that your system can read them. Okay, so I stop at this slide, which is noise.